Hello friends, today we are going to discuss about the balancing of rotating mass in this particular portion of the kinematics and theory of machines. The subject code is PCME 503 and today we are discussing on module 7. For balancing of rotating mass, we know that there are two types basically. One is static and one is dynamic balancing. Now balancing of single rotating mass by balancing masses in the same plane and in different planes, they are done, and balancing of several rotating mass by balancing masses in same plane and different planes, they are also done accordingly. Question comes that what is balancing? Now often an unbalanced component of forces is produced in rotary or in reciprocating machinery due to the inertia forces associated with the moving masses. This is very common in case of engines, different types of engines, because we know that the crankshaft, it is not of regular shape and size. It has got slightly not a very conventional way of geometrical shape. So when different connecting rods are connected at different points, then definitely an unbalanced situation will arise. To balance that situation, we need to take the help of balancing of that particular thing. Now balancing is the process of designing or modifying machinery so that the unbalanced component is reduced to an acceptable level. If possible, it is eliminated entirely. Sometimes in conventional machinery, we could actually nullify or eliminate the unbalanced forces which are generated during the rotating action, but sometimes also it may happen that a portion of that unbalanced forces, they still remains, although they are negligibly small or very minute in magnitude, but still they remains. Now the question comes that why it is necessary. It's a very important thing that the high speed of engines and other machines is a common phenomena nowadays. So it is therefore very essential that all the rotating and reciprocating parts that should be completely balanced as far as possible. If we consider the case of a connecting rod, then after proper study and observation, we must understand that one end of the connecting rod, they used to perform pure rotation, and the other end they used to move by providing a simple linear reciprocating action. Just imagine the situation that a mechanical link for which one end is creating pure rotation and the other end is in pure reciprocatory linear action. So how could we find out that where exactly and when exactly the unbalanced force situation is generating and how to eliminate that unbalanced force? That is a very tricky question. Now if these parts are not properly balanced, then the dynamic forces, they are set up. These forces not only increases the load on bearings and stresses on the various members, but also produce unpleasant and even dangerous noise and vibrations. The following cases are important from the subject point of view, that is balancing of a single rotating mass by a single mass rotating in the same plane, balancing of a single rotating mass by two masses rotating in different planes, balancing of different masses rotating in the same plane, and balancing of different masses rotating in different planes. In this video, not all the situations that I am going to explain, because otherwise the video will be long enough and could be boring. So only the important part that I am going to discuss. For example, balancing of a single rotating mass by a single mass rotating in the same plane. If the situation is something like that, then just look at the figure on the right hand side. Here consider a distributing mass M1 which is attached on the soft shaft rotating at omega radian per second as shown in the figure. Now let R1 is the radius of rotation of the mass m1, that is the distance between the axis of rotation of the shaft and the center of gravity of the mass m1. Now we know that the centrifugal force exerted by the mass m1 on the shaft, that is Fc1, that is m1 omega square r1. This centrifugal force acts radially outwards and thus produces bending moment on the shaft definitely. Now in order to counteract the effect of this force, a balancing mass m2 may be attached in the same plane of the rotation as that of the distributing mass m1, such that the centrifugal forces due to the two masses are equal and opposite. Now let us consider R2 is the radius of rotation of the balancing mass of m2 as we have discussed. So centrifugal forces due to the mass m2, that is Fc2 equal to m2 omega square into R2. Now equating these two, if they wish to nullify each other, then we get m1 omega square r1 that equal to m2 omega square r2. Because they are actually placed on the same rotating shaft, so omega are same on both the cases. So eliminating the term omega square from either side, we get m1 r1 that is equal to m2 r2. Now note that the product m2 r2 may be split up in any convenient way, but the radius of rotation of the balancing mass m2 is generally made large in order to reduce the balancing mass m2, and the centrifugal forces are proportional to the product of the mass and radius of rotation of the respective masses, because omega square is same for each mass as I have told. Next situation, that is balancing of a single rotating mass by two masses rotating in different planes. In the previous arrangement for balancing gives rise to a couple which tends to rock the shaft in its bearing. Therefore, in order to put the system in complete balance, two balancing masses are placed in two different planes parallel to the plane of rotation of the disturbing mass in such a way that they satisfy the following two conditions of equilibrium. Now what are they? The following two possibilities may arise while attaching the two balancing masses. Number one, the plane of the disturbing mass may be between the planes of the two balancing masses, and number two, the plane of the disturbing mass may lie on the left or right of the two planes containing the balancing masses. Now one of the situation that I have shown over here, that is, for example, L1, L2 and L, they are given as, that is the distance between the planes A, capital A, which is just shown at the center on the left hand side of the figure. So distance between the plane A and L, which is given, and L2 is the distance between the plane A and M, while L is the distance between the planes L and M. Now in the front view and in the side view, how does they look like? It is also shown. Important thing to note that for M, the radius of rotation is smaller. For M1, the radius of rotation is R1, and for M2, the radius of rotation is R2. That is very important. Now we know that the centrifugal force exerted by the mass in the plane, that is Fc equal to m omega square r. So similarly we are getting Fc1 equal to m1 omega square r1 and Fc2 equal to m2 omega square r2. Now if we place this mass in such a way that Fc equal to Fc1 plus Fc2, because these two, that is Fc1 and Fc2, these two are the counter affecting forces, balancing forces, those who will balance Fc, that is the disturbing force created by some disturbing mass with a particular radius of rotation, then definitely we are going to get the equation like that, as equation 1 given, that is m omega square r equal to m1 omega square r1 plus m2 omega square r2, or after the elimination of the term omega square we are getting m into r equal to m1 r1 plus m2 r2. Now in order to find out the magnitude of the balancing forces in the plane L, capital L, for dynamic force and on the bearing Q on the shaft, now taking moment about point P, capital P, which is at the point of intersection of the planes capital M and the axis of rotation. Therefore we are going to get Fc1 into capital L, that is equal to Fc into L2. So we are going to get that m1 into omega square r1 multiplied by L, that is equal to m omega square r multiplied by L2. On simplification, we are going to get m1 r1 L, that is equal to m r L2, or m1 into r1, that is m into r into L2 by L1. Sorry, L2 by L. That is equal to equation number 2, that is m1 into r1, that is m into r into L2 by L. Similarly, in order to find out the balancing force on the plane capital M, the same way we could find out, that is m2 into r2, that is equal to m into r into L1 by L. That is equation number 3. Very important thing to note that the equation 1 represents the condition for static balance, but in order to achieve dynamic balance equation, that is 2 or 3, it must be satisfied. So static balancing and dynamic balancing, how they are done, they are shown in this particular 3 equations. Moving forward to a more realistic situation like balancing of several masses rotating in the same plane, as it happens occasionally, then considering any number of masses, say 4 over here, magnitude m1, m2, m3 and m4 at a distance of r1, r2, r3 and r4 from the axis of rotating shaft, and let us also consider that with a neutral x-axis they are creating an angle of inclination in the anticlockwise direction with theta 1, theta 2, theta 3 and theta 4 respectively. Then as shown in figure, let us consider these masses are actually placed in such a way in the space diagram as shown, and this particular shaft on which they are attached, we are taking the view that is not perpendicular but along the axis of the shaft, that is through the z axis, the observer, that is we are observing from along the z axis or through the axis of the shaft or along the axis of the shaft. So therefore the magnitude and position of the balancing masses may be found out analytically or graphically as discussed just on the other slide. But remember that analytical method, according to your syllabus, analytical method is not acceptable, only graphical method is acceptable, and that also you have to solve during the examination in that way also. So that is why I am going to show the way of solving this type of problem by graphical method only. So in graphical method, what you used to do, first you have to draw the space diagram with several masses as shown in figure, then find out the centrifugal forces, that is the product of the mass and the radius of rotation. Remember, you need not to multiply omega square each and every time, because all the terms containing m 1, 2, 3, 4 etc. and r 1, 2, 3, 4 etc. they will be having the same omega, that is the same angular velocity term. So that is why no need to multiply repeatedly with omega or omega square over here. Now we have to draw the vector diagram as shown in figure B over here, downward right hand side, that is the product of the masses of the radii of rotation and the mass, such that the AB represent the centrifugal force exerted by the mass m1 over here, then BC that represents the centrifugal forces exerted by the mass M2 and so on. Now how to find out that what should be the length, the inclination, etc. The point to be remembered or to note over here that whatever may be the direction or inclination of each individual masses, like for M1, the line of action or the angle created, that should be same in case of the vector diagram. At that moment, what is the position of M2, which is making 90 degree or perpendicular on the x-axis, that also shown over here. Whatever may be the inclination angle, that is theta 3, that should be same in case of CD or FC3, and that is also true for FC4. So the same way we have to construct or we have to draw this vector diagram. Now finally this diagram will end at point E. So it will be an incomplete diagram. Accordingly we are going to get. So what you have to do, that in order to get the resultant centrifugal force or resultant unbalanced centrifugal force, we have to connect a straight line from A to E, point A to point E. This particular point will represent the resultant unbalanced force. So whatever may be the scaling factor we have used, multiplying by the scaling factor, we are going to get that the resultant vector force M into R. Now let us discuss this particular thing using a numerical problem. Over here, 4 masses M1, M2, M3 and M4, they are given with a value 200 kg, 300 kg, 240 and 260 kgs, and their radius of rotation, their angular orientation, etc., everything is given. Now in the problem it's asked that find out the position of the magnitude of the balance mass required if the radius of rotation is 0.2. Now first of all you have to draw the space diagram as it is shown over here in the first step. In the second step we have to find out that what are the individual M1 into R1, M2 into R2, M3 into R3, M4 into R4 values. And remember, all the terms should be found out in terms of kg and meter. Whatever may be the unit they are using, try to convert it into kg meter particular form. It will be easier for you to calculate and to understand. Then because we are using the graphical method, then we have to construct the vector diagram. So in vector diagram, using suitable scale, that is taking 10 kg meter equal to 1 centimeter or 10 millimeter, we are going to construct the vector diagram. That is from A to B, we have got 40 kg meter, so 4 centimeter we have to take. Then from B to C, it is having an inclination angle of 45 degree and the length should be equal to 45 millimeter or 4.5 centimeter accordingly. Then C to D, that is M3 into R3, that is 60 kg meter and it is having an inclination angle of 120 degree. So accordingly we have to take it, and then 78 millimeter or 7.8 centimeter length we are going to take for the case of M into 4, that is 78 kg meter particular value, centrifugal force value. So finally what we are going to get, that is the resultant unbalanced force value, that is equal to 23 millimeter. So 23 millimeter represents 23 kg meter. Now in the problem it has been given itself that this particular unbalanced force are to be balanced by a balancing mass which is having a radius of rotation of 0.2 meter. So that balancing mass M into 0.2, that should be equal to 23 kg meter. So solving this, we are going to get the value of the balancing mass, that is the weightage of the balancing mass, that should be equal to 115 kg, and that should be the answer. Now for finding out what should be the angle of inclination of the balancing mass, what we have to do, simply we have to increase this line E to A. Remember, not from A to E. E to A, just reversed direction of A to E, and with the neutral axis, that in this particular problem we can consider that AB is the x-axis. So with respect to that, if we take the angular position of this particular line B to A to E dash, where E dash is the position which lies along the same line E dash, where AE equal to AE dash, and AE dash is 180 degree apart of AE, then the angle that we are going to get, that is 201 degree. So thus we can find it out. Try it. Now balancing of several masses rotating in different planes, this particular type of problem are a bit tricky. And remember, over here, along with the centrifugal force or unbalanced centrifugal force, unbalanced centrifugal couple, they also will arise and appear. To compensate unbalanced centrifugal force along with centrifugal couple, minimum 2 balancing masses will be requiring. Not only one single balancing mass is sufficient to balance this type of situation. So over here, this type of table that we have to construct for the sample problem over here given, that we can see that is in different planes, different mass is distributed like 1, 2, 3 and 4, and in between 1 and 2 there is one reference plane or RP, where one balancing mass will be kept, and between 3 and 4 another will be kept. The individual length from reference plane L, that is also given, that is L1, L2, L3, Lm and Lr, etc. Remember one thing, whatever may be the length we are considering with respect to reference plane, in the right hand side that is considered as positive value, and whatever in the left hand side we are considering, that has to be considered as negative value. So for the sake of our calculation, more values that we can keep on the right hand side, more positive values will appear and less amount of negative values that we are going to get. A sample numerical problem is given over here for a shaft carries 4 masses A, B, C, D, and the values are also given as 200 kg, 300 kg, 400 kg, and again 200 kg, etc. with a radius of rotation 80 mm or 0.08 meter, 70 mm, 60 mm and 80 mm respectively. So everything has been converted in terms of meter, while radius of rotation on the balancing masses, they are also given as 100 mm. Now in this problem they are asking to find out the location and the magnitude of the balancing mass. So first we have to draw properly using suitable scale the position of the planes and the space diagram, that is the angular position of the masses accordingly. Then we have to make the tabular column just like this. So first A, then X, which is considered as reference plane, then B, then C, then Y, that is also the plane for the balancing mass, then D. And important thing to note that in the second column, that is for the mass in kg, mx and my, that is unknown. Then comes the third column where every value is known, that is the radius in terms of meter. In the fourth column that is the centrifugal force divided by omega squared, that we are going to get the m into r value, mass into radius of rotation value. So over here what exactly we are going to get, that is nothing but the mass 200 into radius of rotation 0.08, that is equal to 16 kg meter. Like that, for each and every value we are going to find out the values, individual values. Important thing to note that mx and my, these two values are unknown over here, so they are written as such. Now distance from the reference plane, individual reference plane, which is also given in the numerical problem, so that also is converted into meter and they are written accordingly. Remember, in this type of problem, the sixth column, which is the column of the couple polygon or couple vector, whatever you call it, for that purpose only one unknown value is found, whereas in the fourth column, that is force polygon or force vector column, we are going to get two unknown values. With two unknown values for one simultaneous equation, it is not easy to find out the two unknown, but only one unknown, that we can find it out. So we are going to draw the couple polygon as per the data that we are getting from the sixth column. Over here, important thing to note that minus 1.6, that is the first value. So starting from 0, it will not go in the right hand direction, but just in the left hand direction it will come. So from O dash to A dash, it will be minus 1.6 kg meter square. Okay. Using suitable scale, we have to construct the couple polygon as per figure C. Important thing to note that this particular set of lines, they will end at D dash. So we have to draw a line which is connecting O dash to D dash, and that is actually the direction of the balancing couple or the unbalanced couple. If we are going to draw the line from D dash to O dash, it will be the direction of the balancing couple, or if you want to find out the line O dash to D dash, that is the summation of all the unbalanced vector, then it will be unbalanced couple. All in all, the balancing couple and the unbalanced couple, they will be equal in magnitude but just opposite in direction. So likewise, multiplying with the scaling factor, we can find out what is the value of the unknown my. So accordingly, my value, that is 182.5 kg, that we can get, and also mx value that we can get by putting this value of my into fourth column. Only one unknown, that is mx, will be remaining over there, and just like that, if we draw the force polygon, we can find out the value of mx, and that is 355 kg. Now for finding out the angular orientation of these particular things, simply just we have done in the previous case, 12 degree and 145 degree, these two are the values that we are going to get in terms of theta y and theta x value, that is the angular orientation or angular position of the two balancing masses. Now another problem that is also very important, that is in case of a shaft with bearings in this type of situation. Over here, a shaft is supported in bearings 1.8 meter apart and projects 0.45 meter beyond bearings at each end. The shaft carries 3 pulleys, one at each end and one at the middle of its length. The mass of each pulley is 48 kg and 20 kg, and their center of gravity are 15 mm and 12.5 mm respectively from the shaft axis. The center pulley has a mass of 56 kg and the center of gravity is 15 mm from the shaft axis. If the pulleys are arranged so as to give the static balance, then determine number 1, that is relative angular position of the pulleys, and number 2 dynamic forces to produce on the bearings when the shaft rotates at 300 rpm. Now almost all the data are given, so we have to convert each and every millimeter value into meter, and omega value that we have to find out from the rpm. So let us consider that ml and mm are the masses at the bearings L and M, and RL and RM are radius of rotation of the masses L and M respectively. Now on the plane of L we are considering, that is the reference plane, for which left hand side is negative and right hand side is positive. So by putting all the values over here also in the same way, just you may pause the video over here repeatedly, and you can find out that how the force polygon and couple polygon are constructed simply in the previous way, and we can find out the situation in this method. So this is the dynamic forces at the two bearings, and that's all for today's class on balancing of rotating masses. I hope you will you will practice repeatedly, and you can have a very good concept on this particular chapter, on this particular topic. All the very best to you. Thank you very much.